Now we're going to go back to our little picture here. I have here my capacitive sensor, right? I have here my fixed resistor, and I have here what I'm applying, right, which is like a source, right? Or the energy, the source that we're putting in. And what I've explained to you is that if I set my function generator to DC mode, irrespective of if I set it to 1 volt or 10 volt or 100 volt, it's going to be a very unfortunate instrument. Instead, what I would like to do is I would like to set it to a situation where it's now oscillating, right? And that is how you build, right? Obviously, there's a little bit more information I need to add here. That is how you build circuits with sensors in them. You need a voltage divider, as we've done before, with the caveat that this thing here has to be a sinusoid and not a DC, because if you use a DC, you're going to be staring at it all day and the voltage isn't going to change. Okay, so let's work that through a little bit more to try to understand what the sinusoid buys us. The reason I'm going through this so slowly is that once I actually give you the solution, it's actually really quick. Like I could have just given you the solution for how to solve this. There's a very simple recipe. And when I give it to you, it's going to take about 5 minutes to explain it. I'm deliberately not giving it to you because I'm trying to motivate it. All right, I'm trying to motivate the solution that I'm going to give you. I want to make sure you understand what we're talking about here, okay? But I just want you to know everything we're giving you now, it's not on a quiz, it's not on a test, it's not in any background. I just want you to walk through that. I want you to understand what I'm thinking, all right? So just follow me through for the next 15 minutes. All right, as I continue to tell you things that are quite possibly extremely obvious to you. I want to go back to Ohm's law. And I want to be a little bit more sensitive now to time. So what I'm going to do is I'm going to look at time here. And I'm going to look at this voltage. I'm going to call it V sub R for voltage on the resistor. And this voltage is some value, V sub R. And it's there all the time. I mean, we never really thought about it this way before, right? But when I say that there's a voltage here, and that voltage is 5 volts, what I meant all along was it's just 5 volts all the time. Like 5 volts, you know what I mean, right? It's always 5 volts. And so if you were to look at it in time, this is what we mean when we say there's 5 volts, right? You could also think of this as saying, well, it's a DC voltage. It's not changing. But I never showed it this way because it was sort of seems like an extra bit of confusion, right? But now I want to talk about time. Okay. I now want to ask the question, and I'm going to call this I sub R to be specific. What is the current over this period of time? Okay, so still time. And here I have, and now the question is, what is I sub R? All right, well, and if it's useful for you to think of these as units, think of this as 1 second, 2 seconds, 3 seconds, right? If that's easier for you, I haven't put any units here. Well, let's think about it. And again, I want to emphasize again, I know that what I'm saying is so obvious that even talking about it makes it more complicated, but we need to go through this, right? At this point here, well, I do want to use now values to make it. I'm going to say that the voltage was 10 volts. And I'm also going to tell you that the resistance was, let's say, 5 ohms. Okay. So at this time point here, the voltage is 10 volts. So at this time point here, what is the current? 2 amps, right? So I'm going to say at this time point here, here, I didn't quite align it right, we are at 2 amps. And at this time point here, of course, is the same voltage. So it's the same current, and it's the same voltage, it's the same current, it's the same voltage, and the same current. And so what we can see is, perhaps obviously, is that the voltage is steady, and so is the current. It's why we never brought up time, right? Because it didn't come up, right, in this case, right? But now I do want to bring up time. So now I'm going to give you a different voltage. Now I'm going to say in this example, V sub R, let's stick to the purple here. Looks like this. So it is a sinusoid. Why is it a sinusoid? Because I have my function generator, and I put a sinusoid across this voltage, right? So instead of applying a DC, I now applied this. This is my input. And we can certainly ask the question, what is the output? So now we're looking at I sub R. What is it? What is I sub R in this case? Well, now we have to be a little bit more attentive to timing, because it does matter. And to keep it simple, I'm going to say that the peak value here was 10 volts. And here was minus 10 volts. Okay? So it's going from 10 volts to minus 10 volts to 10 volts to minus. What's the current doing? All right. Let me start right here. At this instant right here, at the moment when the voltage was 10 volts, there's 10 volts across this resistor, and therefore the current is going to be 10 volts divided by the resistance. And so at this time point here, I'm going to have 2 amps. Okay, that sounds like before. But here, at this point in time, well, it's not positive, it's not negative, right? The applied voltage is actually 0. So at this instant, the voltage across the resistor is 0. There's no voltage across the resistor. So what's the associated current? Also 0. So here, I'm at 0. Oh, okay. Now the voltage then becomes minus 10 volts. So now I'm interested in this point here. Okay, well now there's 10 volts. What's the current? Now, we need to be a little bit careful, right? Because we have 10 volts, but 10 volts like this, right? So it's from here to here. So it's really, if we're applying Ohm's law in this direction, VR in this case is minus 10 volt. And therefore I is minus 2 milliamps. You could think of it as 2 milliamps going this way, or think of it as minus 2 going this way. But it's important to recognize that at this point, we are down here, right? Right, the current has reversed. And then, of course, back to 0. And if you were to follow this analysis through, you would get that. So because the voltage is a sinusoid, the current is a sinusoid. And what's more, when the voltage goes up, the current goes up, and when the voltage goes down, the current goes down. The frequency of the current is the same as the frequency of the voltage. You see that intuitively? Now, I drew all this very carefully, but of course, we didn't need to, because we could have used Ohm's law, right? We could have used Ohm's law. So let's give this thing an equation. Now I'm going to give V sub r an equation. I'm going to say that V sub r as a function of time is equal to, well, we know it's 10 volts. And let's just do sine of whatever. I'm just going to, because I didn't put any time here, I'm just going to say sine of 2t. You can figure out what the actual units would have been, right? This was the input. So now the question is, what is the current? And now we have to be a bit careful, because we have to say the current is also a function of time. Well, IR of t, right, is going to be, according to Ohm's law, VR of t divided by R. All right, or R times I of t is equal to that. Right? VR of t is equal to IR of t times R. These are the same. You could say, but then why didn't you mention time before? Because we didn't need to. It didn't matter. It was kind of silly to do it in this case. So I didn't know it was right, but this is correct. At any given moment in time, if the voltage is changing, then the current will track it, and vice versa. And so we can write this, and so from this we divide by 5 ohms. So we go to divide by 5, right? So we can write it out. V of t divided by 5 is equal to 2 volts sine of 2t. Right? I could have, and so what does this tell us? However fast the input wiggles, the output wiggles the same. Like if this was 12.2, the number that would have shown up here is 12.2. If the number here was 1983, then the number here would have been 1983. According to Ohm's law, right, if you put a sinusoid in, we get a sinusoid out. And not only that, the sinusoid out, okay, has the same frequency as what we put in. I don't want to write it out, but if I put 20 here, you see that there would be 20 here. Now, what about the amplitude? Well, the amplitude can change. I mean, for one thing, I'm going from voltage to current, so the units change. But you could see that I could have put in 10. And if I'd put in 10 here, right, ooh. Amps. This is amps, okay? If I put in 10, I would have had 1 amp. And if I put in 100, right, yeah. If I put in 10, I would have had 1 amp. So what can change? If it's a sinusoid in, I'm not going to get a triangle wave out. Do you see that? Or a square wave out. If I put a sinusoid in, I get a sinusoid out. You with me? But if I drew this a different way, right? If I drew another sinusoid, do you see that we would get another sinusoid, right? If I put a sinusoid in, I put a sinusoid out. I get a sinusoid, right? The other thing you see is the frequency of the sinusoid in determines the frequency of the sinusoid out. You see that as well? Whatever I put in, I can't change the fact that it's a sinusoid, and I can't change its frequency. The only thing I can change is how big it is. The only thing I can change, and that is sinusoidal steady state analysis. Except when you taught, it was like a lot more complicated, wasn't it? Okay? Sinusoidal steady state analysis means a sinusoid comes in, and the thing that has to come out on the other end is also a sinusoid, part 1. part 2 is the frequency of the thing that you bring in is the frequency of the thing that comes out. You don't have control over it. The only thing you can control is whether it gets squashed or expanded. And they call it sinusoidal steady state analysis. Because it's sinusoids, and things are kind of going steady here, and we're analyzing it. Got it? Except, you know, we could have done it a lot quicker, of course. I mean, I know it's so obvious, right? It's so obvious, but now you understand this notion of ever heard of things like people talk about linear systems? Oh, it's linear, it's not linear. A linear system, if you put a sinusoid in, you get a sinusoid out, and the sinusoid in has a certain frequency, the sinusoid out has the same frequency, but it can get squashed or expanded. Linear system. So yeah, this is a linear system. We don't need to really use that term here. Okay, but that's a linear. So far, so good? Let's do another example. Let's try to avoid erasing things in case I go back to them. Here's another example from circuits. I have a circuit. The input here, Vs, is equal to 20 sine of 7t. I'm using just odd numbers on purpose, right? Because this could have been any numbers. You shouldn't be intimidated by the fact that there's a number, right? This resistance here is 1 ohm. And this resistance here, well, now I'll use simple note, is also 1 ohm. What is V out? What's that? You maybe already have done this in your head, right? Well, I don't know, there's a lot going on here. Because this is wiggling, and then there's like a circuit, right? But we happen to have an equation for the circuit, don't we? It is V out is equal to Vs times, and if we were to write out the actual values, right, it's going to be 1 ohm over 1 ohm plus 1 ohm, right, would be is equal to Vs times 1/2. That's the... I said, but wait a second. Am I trying to play a trick on you? We did this before, right? I said you can't do it, right? Before I said, remember the capacitor? I said you can't do it, and why can't you do it? Why can't you do it with the capacitor? Because you can't do Ohm's law. But here, it's not true. Ohm's law is still working. The way you derive this equation, if you're right, is by applying Ohm's law, right? I don't want to go through it again, right? So the voltage divider equation, just like Ohm's, it's just if you have Ohm's law, you have this. This is still in effect, and so therefore we can write, well, V out is equal to 20 times the sine of 7t times 1/2, or 10 sine of 7t. Sinusoidal steady state analysis. That's just sinusoidal state. And let's do the check. The input was a sinusoid, right? Now in this case, the input is a voltage and the output is a voltage, right? No problem. So in this case, the input was a sinusoid. Was the output a sinusoid? Check. The input had this frequency, right? The frequency is governed by the number before the t here, right? Does the output have the same frequency? Check. Did the size change? So these were sort of our fixeds, right? Did the size change? Yeah, the size changed. Because that's allowed by sinusoidal steady state analysis. But what you can see is I didn't put in a sinusoid and get out a square wave. I didn't put out sine of 7t and get out sine of 37t because sinusoidal steady state analysis doesn't allow it. All right? Now there's another way I could have done this, which would have been really annoying. What I could have done is I could have drawn out the voltage at every given point, right? And then said, right here, let's apply the voltage divider equation. And then right here, let's apply, right, when the voltage is zero, the voltage is zero, let's apply the voltage divider equation. Well, then that's zero, right? I said, okay, here the voltage is negative, so the voltage is negative. Now we could have, and you would have gone the same thing, right? We would have arrived at 2 wiggles, right? And in this case, I'll use this right here. I'm not referring to this circuit, right? The output is simply half of the input. And that's sinusoidal steady state analysis. It's not, that's all, it's just telling you how to deal with sinusoids. So far, so good? Yeah? Great. Here's another one. Same thing, right? We're going to use the small space here. Now there's a capacitor. And this capacitance has a capacitance value of 1 farad. But to be clear, this is a capacitor. Okay. What's V out? Well, here's the wrong thing to do, right? The wrong thing would be to say, okay, well, I mean, before it didn't work, but now I'm sure it will. Right now it's fine because it's a sinusoid, so I'm going to just write that V out is equal to Vs times, it's going to be 1 farad over 1 farad plus 1 ohm, right? And never mind that, you know, you have farad here and ohm here, so the units don't protect. You can't do it. You can't do it because you can't, it continues to pretend like this C is a ohm, right? Even though we have a sinusoid here, that does not forgive you from just pretending like this wasn't you can't just, it's not a capacitor, it's a resistor. So now I'm going to just go ahead with it. This is incorrect for the same reason that you can't write, right? You can't write Ohm's law over a capacitor. This is the equation that determines what happens over a capacitor. Does that make sense? So I haven't given you the solution yet, right? But I'm just getting you, but this certainly is not the solution. I mean, again, it wouldn't even make sense, right? What's a farad plus an ohm, right? You can't add those things together. I mean, let's go back to our capacitor. And we have a voltage across the capacitor. I'll call it V sub C. And we have a current across our capacitor. And we know that I sub C is equal to dV of C, dC, dt. That is the equation, right? Let's think about it. So now, well, I'll do this one quick. I'm going to apply, didn't have to erase it, a fixed voltage. I'm just going to make it 10 volt. So this right here is V sub C, and I'm applying 10 volts. And of course, as I asked you before, we can ask what's the current? And now we're thinking about time. Boom, 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 boom. All right, well, what is it? Well, maybe you remember a little bit, right, about that, when you have something that doesn't change, right, it has no slope, and in fact, its derivative over time is 0, right? If you put in a constant, right, and you take its derivative, you get 0. There's no dv dt here. It's fixed. This term here, as I was trying to explain before, is a 0 term. There is no change in voltage over time. Maybe put it another way, right? The voltage is not changing over time. The amount of voltage change over time is 0. All these things are true, right? However you want to get it. So what that means is that the current in this case is 0. Now you'll notice that this 0 doesn't depend on the capacitance. It's 0 no matter what. If you put a 9-volt battery across the capacitor, there will be no current flowing across the capacitor. All right? But that wasn't true for a resistor, was it? Right? It was a little different. Okay. And that's something we talked about before, right? So we talked about before, right, that this is 0. Okay. Let's go to our sinusoid. Now let's see what happens. So now we have V sub c, and I'll make sure we're talking about time, right? And it goes up and down and up and down forever, right? Okay. And we can ask the question. I could have drawn this in orange. I did the orange last time. I'm going to ask the question, what's the current? We're doing, by the way, sinusoidal steady state analysis, right? Sinusoids in, what comes out, right? Okay. And I think you may already see where this is going. But I think it's nice to track it. I don't know, for me it is nice to track it. 1, 2, 3, 4, 5. All right. Well, I'm going to start here. All right. So here's the point I'm interested in, right? And I want to know what the current is. I cannot just take the voltage, right? I have to ask, what is the change in voltage? What is the slope of this line at this point, right? And if you remember a little bit of, I don't know, when do you get this? Calculus, right? Or, right? You'll realize that right here, even though we're at the peak, right, of the voltage, we're actually at a plateau as far as the change in voltage. Oh, okay. So actually, at this point, dV dt is 0. That means the current is 0. So that's this point here. Well, that's not what we saw with the resistor, right? That's definitely what we saw with the resistor. When the voltage is high, the current is high, right? Here we're saying where the voltage at the current is 0. And in fact, if I were to jump all the way to here, once again, even though this is the plateau, right? From a calculus perspective, from a change perspective, there's no change here. So this would be also 0. What? And then I start poking around here and I say, okay, well, what about, I want to jump right here. So at this point, what's happening is I'm at 0 applied volt, right? This is 0 volts. So if this was a resistor, it would be associated with 0 current. But it's shooting up. So actually at this point, even though the voltage is 0, I don't live in voltage world, I live in derivative world, right? So this is actually a point of positivity. And in fact, it's going to be the point of maximum positivity. Oh. And here is another interesting point, because here the voltage is again 0. So if it was a resistor, it would be 0 current, but it's not a resistor. And there's a big decrease in current here. And it turns out that I have a value here. And if you were to connect these lines together, you would see in orange the outcome. Here's 0. There it drops down again. Okay. Not the cleanest picture, but I want you to draw a couple things out of it. The first thing was that something's happened. There's like a shift. There's like a shift, right? Like here where it's peak, it's a 0, and actually when this one's a peak, that one's a 0. A little bit interesting, right? A little bit interesting here. Now, I didn't actually talk about the amplitude of it, so I'm going to give you that in 1 second. All right, well, could I have just saved us all a lot of trouble and just written out Ohm's law? Well, no, because Ohm's law doesn't apply, right? But I could have written this. So what does that mean? It says that I of C of t, I of C of t is equal to, right, this function, which I didn't give you the function, but what was the input I get? What was the input last time I had? It was 10. What's that? 20 sine of 70? 70, right? And I'm going to want to take the derivative of this function, right? So derivative of all this with respect to time times the capacitance, which in this case, I'm just going to tell you, let's say that it was, well, 1 farad is what we had all along. 1 farad. So the current is equal to the derivative of the voltage times the capacitance. Right? That's what this equation tells us. And I have an equation here for the voltage I applied in. Right? I have an equation here, right? This is 20 sine of 7t. So what is that? Do you remember? What's the derivative of a sine? Cosine. What's the frequency of the sine? Same as the sine. Right? The derivative sine of A is equal to cosine of A, but 7 comes out, right? Oh, 7t, thank you. 7t, and then here I'm going to have, well, the 20 comes out, and then I'm going to put my 7 here, and all this is times 1f. Is there a negative here? Is it a negative sign? What's the remember that identity? Is it a negative?
No, that's cosine into sine. The next one would be negative.
Okay, so sine into cosine is not negative. All right, so here we have our result, which is, which is 20, which is going to be 140 cosine of 70. If I did it right, okay? So you'll notice that the thing that came out, right, is a sinusoid as well, right? But you'll say, but wait a second, I went from sine to cosine. You're allowed to do that in sinusoidal steady state analysis, okay? It's equivalent to sort of a shift in phase. So the first rule of sinusoid steady analysis is still fine. Sinusoid in, sinusoid out, right? And we could have rewritten this as a sine if we wanted to, right? So that's the first thing. Sinusoid in, sinusoid out. Second rule of sinusoid steady state analysis, the frequency doesn't change. 7t and 7t. The rate of the up and down wiggles of the voltage and the current are the same. Sinusoid in, sinusoid out. However, the amplitude, which before was 20 and now is 140, has changed. Now, albeit in this case we're going from voltage to current, right? Right? But we are allowed to change only this term. So you could have just done what I did, or you could have just applied this equation. All right? What you can see about this equation is it respects sinusoidal steady state analysis. Sinusoid in, sinusoid out. 10 hertz in, 10 hertz out. 100 hertz in, 100 hertz out. It doesn't do anything that violates this thing that I'm calling sinusoidal steady state analysis, right? But you can see it does transform it. The other thing you can see is that whereas when you apply a battery to a capacitor, you get no current. When you apply a sinusoid to a capacitor, you do get a current. It wiggles at the same rate as what you put in. So whereas batteries don't really seem to be very interesting when it comes to capacitors, once you add this in, it does matter. And I also want you to notice that the output here does depend on the capacitance. Right? In this case, the output didn't depend on the capacitance because it was always 0. But in this case, the output does depend on the capacitance. All right. What's left for next class? Well, now let's do this one. All right, that's the final piece of it, right? I'm telling you that to make this work in biomedical instrumentation, you need to put a sinusoid in, not a DC, put a fixed resistor, and put a capacitor. And I told you that then this circuit will work. So what that means is that we need to figure out what is V out, right, in terms of this input, right? And I'm going to show you how to do that. I'm going to show you how to do that without ever thinking about this term again. Even though I went through, right, some differentiation here, we don't actually need that to solve what this circuit does, interestingly enough. The only reason I went through it today is I needed to get some intuition about what this thing is doing, right? It's acting as like this differentiator, right? But it doesn't introduce, and I've also explained to you what sinusoidal steady state analysis is, right? In a different way. Okay.